All right, so we'll talk about local regression, or LOS, which stands for locally weighted scatterplot smoothing. So the LO, locally weighted scatterplot smoothing. Developed back in 1979, but it's a non-parametric regression method in that we're not trying to fit one model to the data. We're not trying to fit one, relationship between X and Y. We do what's called local regression, and just kind of a quick example of what this could look like. So here's we'll look at this again later, but here's some data, and basically it's just kind of fitting a line that looks like it fits the data. And this is not a quadratic line or anything like that. It just says here we got data points here, and we got data points here, and data points here. Let's fit this, okay? And so basically what it's doing is for each X value that we have in our data set, it creates a window, okay? So you can imagine, maybe I'll copy this into a slide here and draw on it. So it's creating a window, and it takes those data points. So let's say here we have, and then so let's say we're going to look at some data point here. Okay, so let's say we want to look at the data points for this X value. Okay, so we create kind of this this window, and you can specify when you run the LOS command, you specify the window, okay, or how much, and sometimes it's like 2/3 of the data or 1/3 of the data or whatever it might be. And basically looking at the data that's inside this window, we create a weighted least squares model. Okay, so the ones near this center point, these are heavily weighted. And then the ones far away that are still inside the window basically are weighted less. And pretty much basically outside of the window, the weights are 0. So they don't even count. Okay? And so for this, we create a model that just says, okay, well, how do we fit this? And then we got like some kind of line that looks like this or something. Okay, and then we go to kind of the next data point, and we do the same thing. We maybe we're looking at data over here, and so we got another window that kind of, this window slides along, and I don't know what's wrong with my picture here, but the window slides along, and we fit another thing to these things. And it goes on and it goes on until we get end up getting the curve that we see here. Okay, and so that's kind of LOS from this just very big picture perspective. The computations behind LOS are actually very complicated, or not complicated, but just very they'll take a while, and so nobody does this ever by hand. Okay, we have the computer program, and it's not even programmed in R. I mean, it's implemented in R, but it's written in C, just for speed, and so so you can't really look at how it's being done. But I've got kind of just this very, very basic example that kind of illustrates how this works, and kind of gives us an idea of where this lowest curve would be coming from. Okay, so I'll save this and. All right, so let's take a look. Okay, so here I'm going to just start off with our data. So our data is just as silly. I got x 1, 2, 3, 4, 5, 6, and then y is 2, 8, 6, 8, 6, 12. Okay, and so if we were to just fit a regular old linear model, it would look like this. Not exactly the best fit. Okay. We can run low-s, okay, and when we do that, it spits out these numbers, and we're like, well, how did it even get any of these numbers here, okay? And if we can plot it, you just do lines, pretty much the lowest function that we have written here, and this is kind of how it's trying to smooth out the data here. Okay, so we have 6 data points, so it consists of five lines here. We're trying to create something between our 6 data points. Okay, and so this is not the exact. You'll see there's going to be a mismatch between the lines I fit and how it's being generated, but this is. And that's because I'm just trying to fit linear models, and you can see I'm subsetting the data, and we're gonna and I'm weighting them. Okay, so basically I'm gonna fit a linear model for the first 3 data points. Okay, data points 1, 2, 3. So I'm just trying to fit these 3 data points. Yes, question? Yeah. Yeah, I'm not. Well, okay, so I'll show you. So there is kind of a small window here. So because I have 6 data points, my window is going to be fairly big. It's going to be like 4 data points. 4 out of the 6 data points are kind of for the edge. I'm using 3 data points. So for the first one, for this first segment here, I'm using the first 3 data points here. Okay, and I'm going to weight this data point heavily with a weight of 3. This one's going to be weighted 2, and this one's going to be weighted 1. Okay, and I recognize this. It feels a little arbitrary, and but we're basically just trying to weight the ones in the middle higher and the ones far away from it less. Okay, and so we're just looking at the first 3 data points, and we're going to try to fit a segment. And it's not going to be perfectly with this, but it's going to be pretty close. Okay, so I've got the lowest. I'm going to fit basically a single linear regression line, and if I fit a single linear model weighted with 3, 2, 1 for these 3 data points, I get this. Okay. All right. Well, because I'm building this incrementally here for you guys, I don't have to run all these other commands. And then so the next part, I'm going to look at the first 4 data points. 1, 2, 3, 4. Okay, and I'm going to weight the second one, value 3. This is going to be weighted 2. This will be weighted 2, and this will be weighted 1. Okay, so the one kind of in the near where I want to be is weighted higher. These ones are weighted less, and you can kind of play around with the weights to see how this goes. The lowest line does all of this. Okay, and so we fit another line right here, and it looks kind of like this. Yes.
So in the weights factor, if you put 1 over 4, 3 over 8, 1 over 4, and 1 over 8. Will it create the same thing?
Yeah.
Okay.
Yeah. Basically you add them up and you divide by the sum here. But yeah, that's the same thing. Saying this one's worth if this one's worth 1, this one's worth double, and this one's worth triple. Okay, so essentially Okay, and then again, the next one, we're going to use 4 data points. So we're going to look at data points 2, 3, 4, and 5. These 4 data points, and you know, it's a little bit arbitrary in the weights, but this will be weighted 2, 3, 2, 1. Okay, so if I fit that and I plot that line, you know, so we can see kind of how the our lowest comes along, and doing kind of following the same method right here. We're going to add this one, and so we got a line right there. And so we only take the segment that's relevant, okay? And so we're kind of getting this piecewise function. And then lastly, you know, just looking at the last 3 data points, 4, 5, and 6, and weighting this one 3, this one 2, and this one 1. We can add that, and we get this kind of thing. I want to make sure this looks the way I want it to look when I render the markdown file. Okay, so yeah. So fitting these all in here, we can see kind of how the lowest function fits this stuff here. Okay, and yes.
So the window size are different for, say, the first, the end part.
Yeah. Essentially, when the weights, I'm trying to remember, all the technical details are written in this. You can read the actual original paper that describes the nitty-gritty of everything. But essentially, yeah, when you get to the ends, you don't have data over here, and so what you notice is that a lot of times the lowest line will can kind of veer off a little bit more than what you might expect if you just have 1 or 2 data points, and that's because these ones just get weighted heavier, and so the window size is actually, it's supposed to kind of remain constant throughout. Just kind of for the simplicity of this example, I didn't quite do that because I wasn't sure how to get how to appropriately do the weights in a simple way here. But so anyway, you do this, and actually it's an iterative. When you run it in R, it is a bit iterative in that the default settings for low-s, and I'll run this, and I'll add a blue line here. So the default settings, if you don't specify iterations, I think is 3 iterations, okay? So I'm going to add a blue line, and it's going to be very close to the red line that exists, but it's also just ever so slightly different, okay? So it's just a tiny bit off the red line that currently exists, and it's because I don't remember, I don't know the details behind the iteration process, but apparently after several iterations it improves the fit or whatever it's trying to deem to be a good what a good fit might be. Okay, so anyway, we would never actually try to figure out these piecewise parts ourselves, not even, you know, it's simple with R, you know, even when we can specify a linear model and we just specify these weights ourselves, but we would never try to do that. But the lowest function that exists in R is good. So you know, here's an example. We can look at the cars data set. The cars data set plots, I'm just going to show you, plots the braking distance and the speed of the car. So how fast was the car going? How long did it take to stop? You know, is there a relationship? Okay, and so if we plot it, it looks like, okay, it looks like there's a clear relationship between speed and distance, and the question is, does it, you know, bend up, or does it just kind of, is it straight? How do we, what do we know? Okay, and so one thing we can do is we can just kind of fit a low S line, okay? And so the low S command in of itself just returns us a bunch of coordinates, and it says, you know, when your x is 4, I'm predicting 4.956 whatever, okay? So somehow it calculates this value based on the x you provide it. So again, we're calculating values. The lowest is calculating values for each x that exists here, okay? And we can throw this into our thing just using the lines command, which kind of just joins all of these things together. Okay, and so this is our thing, and so it seems like there's a little bit of curvature, a subtle curvature in our data here. Okay, there is also kind of a companion function called low s without the w. Okay, so you got low s and low s without the w, which low s without the w is a generalized version of low s with the w, but we have a question.
For low S, so the default is 3 data points?
Three iterations, and the default is to use 2/3 of the data in the for your window. So the window is 2/3 of the entire data wide. That's the default setting, and we can see how changing that window setting affects the shape of the thing. And the weights are all kind of determined internally. So actually, yeah, before I get into, I guess, low s without the w, I think it's worth exploring the commands that we have. Okay, so x and y would be the points in our scatter plot. Okay, f is the smoother span, so it assumes 2/3 to use 2/3 of the data, and iterations. I don't know the technical what exactly is happening when it runs iterations. Okay. I normally just do, if I ever run low s, I just normally leave the default commands, and I'm happy with the results that it gives me. But the f is probably the, if you were to change a statistic or a value in the low s function, f is probably the one that you would change. Okay, so let's go back to our plots here. Okay, so this is, there's not a whole lot of jaggedness in here, so I don't know what how changing low s would affect us. So if I do low s and if I do f is equal to 1/3 rather than 2/3, and we'll put this in blue, and we'll see how this affects. And so you can see it gets just a bit more jagged here. Okay, and if you know, if I shrink this down to something really small, it'll almost be like it's trying to fit every single data point that it can. So you know, when there's only one data point in the win for a certain x value, it fits those almost exactly. Okay, so this is you know, kind of a classic case of overfitting, but you know, we're not. There's no parameters being specified here. We're not getting a function back. Okay, it's not. This is not the function. It's just kind of. It's just giving you. So the original title of the paper was smoothing of scatter plots, right? So it was just trying to create kind of a visual a visual tool to kind of get the overall shape. Okay. But the default using 2/3 and having and the values as they are is it's pretty good in my opinion. Okay. You can fit the generalized tool is LOESS, LOESS without the W. Okay, and this stands for doesn't stand for anything, but they just picked a name that's almost exactly the same. I think if they were to say it stands for it, it would be local regression S. It's terrible, I know. But you can specify the polynomial degree. The degree normally being degree 1 for linear models, but you can try to fit degree 2 quadratic things here and see how that that affects it. Okay, but plotting a LOESS fit just requires a few more lines of code in R. So you fit the you run LOESS and create a kind of a LOESS fit object, and then using that object, then you have to create a prediction data frame. Okay, so just like with a linear model object, you could create a prediction data frame. You do the same thing. You're creating a LOESS model object, and you can create a prediction data frame this way. Okay, so here we'll show this. This is in this is what LOESS does. So it's a little bit, tiny bit more jagged than the low with the W fit. And I'll show you what fitting other degree polynomials will look like. If you change LOESS fit to degree 0, it becomes a moving average. So let's do LOESS fit 0, degree 0, and we'll put this in blue. Okay, so LOESS fit 0. Oh, that looks almost exactly better. Am I going Oh, that's why. I'm like, that looks exactly the same. I did something wrong. Okay, thank you. Yeah, let's okay, let me do this. Yeah, shoot. Okay, so we're gonna fit this, and is that right? I think if you just do the average of 2/3 of the data, it ends up here, and then as you move along and you move that window, the moving average kind of shifts. So it's very I don't know, sluggish to respond, I guess. We can fit, let me just run this and do LOESS fit 2 and do a second degree, and we'll put this one in green. Huh? Oh, I keep doing the same darn thing. Okay. All right. There we go. Okay. So you guys can, okay, it shows it better on that screen than on mine. So you can kind of see the curvy nature of this with the second degree terms in there, and then let's fit back the I need another color here, black. So the one to, so fitting the linear models, we got that. Okay, so anyway, low S without the W, you can fit different polynomial or different, I guess, degree terms in there. And this allows you to kind of make, I guess, give you a little bit more finer tune in the kind of making the predictions and things of that nature. But low S with the W is, I guess, is the simple version, and for if you're just trying to fit kind of a smoothed line into your data, it's not too bad. It's not too bad. All right, so so one application of LOS as a tool to check model fit is you can compare the LOS fit to the model that you have currently proposed. Okay, and if there's a pretty good match between the LOS and your proposed model, then that's a good sign. Okay, so if we look at the salary data, and I plot the salary professor salary data, you know, we get this kind of thing, and so fitting a linear line is clearly not a good idea. Okay, we can try fitting a quadratic term in there. Okay, and that looks a lot better. And so we can compare this, and we can just kind of throw on the low S curve and see how that works. Okay, so that's low S with the W, and let me also run low S without the W. And we'll throw this in here. Okay, so I want let me salary as explained by experience. Okay, so we'll run this. Oh, did I do something wrong? Speed predict. Plus fit. I have to do 143 here? I don't know. I feel like I'm doing something wrong. Oh gosh.
Is it the data frame speed?
Oh yeah, that's what it is. Like, what's going on? Okay, there we go. All right, so let's, thank you. Okay, and let's throw in our okay, so I don't know if you can see this. So the black line is our quadratic fit, and then the red and blue lines are the results of red would be the low S with the W, and the blue would be low S without the W of degree 1. They're all kind of looking pretty similar. I guess I can try fitting degree 2 in for low S fit, and we'll throw that in green and just see how that goes. Okay, so they all kind of match fairly closely. So this is a good sign in that our black line of the quadratic fit seems reasonable. Okay, we can further apply this. Where did my my notes go? For some of the other examples, so we have the defective rate versus temperature data. Let me pull that up. Sorry. Pull the same. Okay, so let's do that and just check. All right, so looking at if we plot defective as a function of temperature, okay, so looking at this, we're not just looking at eyeballing it, it feels like maybe there's some curvature to this. The low S, using the low S as a tool for this, we can just do lines, low S, so the only thing about the low S function itself, you can't specify. My thing is not working. You can't say data equals defects. You can do it with low S without the W, but with low S with the W, you have to do $ notation. Okay, so let's do this. Color equals red. So we'll add that. Okay, and so when we fit the low S, I think it makes it a lot easier for eyes to detect the curvature. Okay, indicating that a straight linear fit is probably not the best tool for fitting defective in temperature. And so using this kind of just as a diagnostic tool in terms of just saying so you have an array of diagnostic tools at your disposal. You have all of those standardized residual plots and all of that stuff. The low S is just another tool in that kind of arsenal in terms of as a way to eyeball if the fit you have is appropriate or not. Okay, because low S, it's non-parametric. It doesn't depend on us specifying whether it's a linear fit or quadratic or that we should do this or that. It just says, oh, let's look at the data, and it kind of the middle of the data is here, so we're gonna try to fit a line here and move about. And of course you can play around with the the width of the window and things like that to see if you want a more jagged or a more smooth option. So you have that going on, and so you can use it in conjunction with the other tools to check your model fit. Okay, what do you call it? The default plot function in R. So if we go back to our professor salary thing, And if I fit the bad model here, okay, fitting a straight line here, and if I run plot on M1, well, the default settings here is to create the residual plot, and this red line here is a low-s curve. So the plot functions in R run kind of low-s, and so it allows you to see, you know, is there curvature or is there a pattern in my data. So it's not trying to fit anything. It's not specifying any parameters here. It fits, these red lines that you fit are low-s curves. Okay, and they appear in that first one, and then they also appear in your scale location plot. So standardized residuals, again, ideally we want this line to be flat, okay, and so when it fits a low-s curve and we see that it's not quite flat, we actually have kind of this W going on here. It goes down and goes back up, and so and then it also fits it to this residuals versus leverage. So, you know, all of these things indicating a poor fit, which is quite clear from this right off the bat. But our plot functions implement using low-s or localized regression as part of the diagnostics. So anyway, yeah, I just wanted to kind of explain how low-s works, and you know, this very rudimentary example at the very beginning is not technically how, you know, if you get down to the nitty-gritty, the calculations are slightly different, but it should give you a good picture in terms of, you know, we're just looking at a subset of the data, we're weighting them so that the data points near the spot that you're interested in are weighted heavier, and then we're fitting a line based on that. Are there any questions? Yes?
But is it the same for ggplot? Like, if we just add that?
Yeah. So the ggplot. Okay, so let me do library ggplot2, and then we do ggplot of our model. So what do we want? We want prof salary. AES is that x equals experience, y equals salary, and we want geom underscore point and stat smooth. What is it? Huh?
Stat underscore smooth.
And I think the default is the, whoops, is that it fits a low-s into it. Is that the same? Does that look exactly the same as the low-s that we had earlier? I don't, maybe the settings for the low-s are just slightly different, but let me just see. Where did I do it? Right here. It looks a little bit different, huh? This one has it seems to fit the tail a little better than this does, or the ends, but pretty similar. Maybe it's doing something different. Okay, but yeah, the default stat smooth in ggplot does some kind of low-s also. I guess we can ask what the geom smooth, let's see what stat smooth understands. Low. Okay, so method to use auto LM, GLM, GAM, low S, RLM. Default is low S without the W. Low S for Okay, so I'm not 100% sure. Well, look, it says it looks like it's saying low S. Low S without the W as its method for fitting a smooth thing. So so yeah, it makes an appearance in a lot of functions and packages because it's a useful tool because it's non-parametric. It makes no assumptions about the data. It just says, here's the data. Let's do our best in trying to fit something here. And so I hope this kind of demystifies a little bit just where these lines are coming from. It is still kind of mysterious because the inner workings of how the weights are calculated and all that is still a little bit cloudy. But you can read, just for fun, if you want, you can read Cleveland's paper, which gets into the details there. Okay, that's all we have. Enjoy your weekend. I'll be busy grading stuff, and I hope to have you guys' grades ready as soon as I can. So, all right, we'll see you guys on Monday.